is 0.9 ohms and shunt field resistance is 200 ohms. Find the efficiency of the machine. Find efficiency of the machine as motor and generator. As motor and generator. When the line current at full load is 21 amperes. Also find efficiency of machine as generator. Also find efficiency of machine as generator when load is half the full load. When load is half the full load. Okay. So given things. Input voltage is 200 volts. Okay. I naught is 2 amperes. Armature resistance RA. This is hot resistance. If it is not mentioned, then we should consider it as hot resistance only. Okay. 0.9 ohms. RSH 200 ohms. So IL or I is 21 amperes. You can take I or IL, both are same. Okay. Now, what should I find? Efficiency of motor, efficiency of generator at full load, efficiency of generator at half the full load. Note here, I have not mentioned efficiency of motor at half the full load because it is not that direct calculation like we see. We can make certain assumptions and do. Okay, we can make certain assumptions and do, assuming that the back EMF will remain constant, and then we can do the calculations. But it is not so. Back EMF will not remain constant when the load varies. Okay, that when we come to that point, I will discuss. Okay, so solution. So first I have to find out what are the constant losses because hot resistance already we know. So once I find constant losses, that can be used for both the efficiencies. Calculation of both the efficiencies, right? So constant losses WC is equals to. Here we need not to use all the concept. Directly we will be using the expressions. Okay. So for that I need to know what is IA naught. So IA naught is equals to, I will take I naught minus ISH. Before this we will find ISH. What is ISH? It is V divided by RSH. 200 by 200. 1 amperes. Okay, so therefore IA naught is equals to 2 minus 1 is equals to 1 amperes. So the no load armature current is 1 amperes. Okay. So therefore constant loss WC is equals to, it is V into I minus IA naught square RA equals to, so V into I naught. So 200 into 2 minus 1 square into RA is 0.9. So constant losses WC is equals to 400 minus 0.9.
399.1.
Yeah. Watts. So almost all the losses are constant losses because IA is very small. Okay, IA naught is very small. This is IA naught square. It is just 1 amperes. Okay, so this is constant losses. So once I know constant losses, I can find the efficiency as a machine, machine as a motor or a generator. So I can take in the next video efficiency as motor. Efficiency as motor. Okay, so whenever you are calculating efficiency as motor, first draw the diagram, whether it is any test, because it will give you a better view. So plus minus, this is I, this is IA, and this is ISH. Okay, now IA is equals to, it is I minus ISH, which is equals to I is 21 minus ISH is 1, so it is 20 amperes. So the full load armature current is 20 amperes. Okay, now motor input is equals to V into I. So 200 into 21 equals to 400 plus 2. 4,000.
4,200.
Yes,
4,200.
4,200 watts. Okay, then armature copper losses. To IA square RA. Okay, so IA we have got 20 square into RA is 0.9. Okay, so it is
360.
360 watts. Okay. Then constant loss we have already calculated is equals to WC, which is equals to 399.1 watts. Total losses in the motor WM is equals to IA square RA plus WC. So this is 360 plus 399.1. 715 point 1 watts. Therefore, motor output. Somebody is waiting to join. People, I think they join whenever they want. Still, people, I think they can give the reason bus late. Motor output. P out is equals to motor input minus losses minus total losses. So this is equals to 4200 minus 759.1. So P out is equals to, let me call this motor input as P in. It is 3440.9 watts. Therefore, efficiency of motor at full load, we can calculate only at full load, is equals to P out by P. Okay. Is equals to 3440.9 divided by 4200. Therefore, percentage efficiency is equals to, I can write, how much?
81.9.
81.9%. So this is the efficiency of the machine as motor. Efficiency of the machine as motor. Okay, now we have to find efficiency as generator. Efficiency as generator. Again, draw the circuit. Now it is generator. As generator, it will give out the armature current. So this is plus minus. And remember, whether it is motor or a generator, terminal voltage is V. 200 volts, whatever is been mentioned, that is V always, terminal voltage. Okay, you should not consider that now voltage V is the generated voltage in the generator EA. It is not like that. Okay, whether it is a machine operating as motor or generator, the voltage whatever is mentioned is always the terminal voltage. If it is motor, it is input terminal voltage. If it is generator, it is output terminal voltage. Okay, that you should keep it in mind. So for generator, IA is equals to I plus ISH. Okay, so the specified current is 21 plus 1, it is 22 amps. Okay. So remember, armature copper losses in generator will be more than the armature copper losses in motor, because armature current will add up with the field current in generator. Okay, whereas armature current will be deducted with field current in motor. So armature copper losses in generator for the same machine will be more than the armature copper losses in motor. Okay. Next, we will follow methodically. So generator output. Now we know what is I and what is V. So I will get generator output, electrical output. Generator output P out is equals to V into I. See whether the machine is now rated operated as motor or generator, the output power is remaining constant. It is 4200 watt machine only. Okay. 200 into 21. So this is 4200 watts. So there is no change in that. Output will be 4200 watts. Accordingly, inputs will change. Okay. And you will observe that the machine efficiency will not be the same. Next, armature copper loss. Is equals to IA square RA. So I is 22 square into 0.9. How much?
435.6.
435.6 watts. Okay. Then constant loss is already calculated. It is 399.1 watts. So therefore total losses WM is equals to it is IA square RA plus constant loss equals to, so it is 435.6 plus 399.1.
834.7.
834.7. Okay. Therefore, motor input, generator input, PN. Electrically, I will be knowing the motor input and I will be knowing the generator output. So there we find motor output by knowing losses. Here we find generator input by knowing losses. So it is generator output plus losses. I will write this as P out plus WM. We know that directly. So P out is 4200 plus WM is 834.7. So this is
5034.7.
5034.7 watts. Therefore, generator efficiency at full load is equals to P out at full load divided by P in at full load is equals to. So it is 4200 divided by 5034.7 into 100. So percentage generator efficiency at full load is equals to
83.42.
83.42. Percent. Okay, so this is the full load efficiency of generator. Now I should find the generator efficiency at half the full load. Generator efficiency at half the full load. Okay. So here we have to recalculate all the calculations what we did for generator. Because when it is half the full load, The current drawn by the load I is I by 2. Therefore, my armature copper losses will be different. Okay. I cannot take directly the losses Wm as it is, just by deducting the, just by making the line current half, I cannot take the losses, same losses as Wm. So this Wm is at full load now. At half the full load, armature current is different. Therefore, losses in generator at half the full load is different. Okay. So it is very much important for us to know what is the losses at half the full load. I cannot take directly the same losses. I should recalculate the losses at half the full load. Okay. So here, armature current at half the full load. Armature current at half the full load. Okay. I can call it as I half is equals to I half plus ISH. This is a generator. Now what is I half? Line current at half the full load is equals to 0.5 or 1 by 2 into line current at full load. So this is equals to 1 by 2 into 21. So that is 10.5 amperes. Okay. Now what is P out? At half the full load, it is I half the full load into V. Okay. So it is 10.5 into 200. So this is 2100. So when I say half the full load means what? Output power is half. Yes or no? Half the full load means the power drawn by the load from the generator is half. So the full load generator power output power was 4200. So therefore my half the full load generator power is half of that divided by 2. But from where I get this? Because the current drawn by the load is half. Okay. So when observe, this is valid only for generator. When there is no load connected to the output terminals, current I is 0. When there is no load connected in the output terminals, current I is 0. Therefore, I can directly multiply the load factor to the line current based on the load condition. The same I cannot do here for the motor. Even when there is no load on this motor, there is some current I not drawn from the source. So I cannot take no load current for a motor is 0. Or 50% of line current is equals to 50% load condition on the motor. This concept I cannot apply to the motors because motor even at no load condition draws some current. But whereas generator, the line current at no load is 0. The line current at no load is 0. Okay, so we should keep it in mind that. Okay. Therefore, the power drawn by the load is also half. So power generated by the generator is also half. Okay. So I have to deduct power also. I cannot simply take the same input power and take the half the output power and calculate. The efficiency will go down very much. Here, remember, I calculated full load efficiency in the previous point. So full load output is 4200. Full load input is 5034. I cannot take 2100 divided by 5034 as efficiency at half the load. We should never do that. Okay. Now I should recalculate what is the input power at half the full load condition, which will be different than 5034 and less than 5034. Okay. So to do that, I need to know what are the armature losses, copper losses at half the full load. armature copper loss at half the full load. You will be doing the same thing in lab. Okay. I have to give some instructions regarding practicals at the end of the class. I will give. Yeah, it is now IA half full load square into RA. Now, which is equals to 10.5 square into 0.9. Yes, what is the value?
99.
99.225.
Excuse me, sir.
Yes.
Sir, IA of in the sense I of plus ISH, it becomes 11.5, right, sir?
Oh, yes. This we haven't calculated, right? It.
Yes, sir.
So this is 10.5 plus 1. Yeah, this is 11.5. Sorry.
Yes, sir.
Thank you, ma'am. Square here. Yes. Sorry. I thought I half itself is 10.5. So it is 11.5 square. So it is 119.025. You take 119. That's. And what were the armature copper losses at full load? It is 435. So is it half of that?
No, sir.
No. Okay, you can't take like that also. You cannot directly divide armature copper loss by 2 at half the full load condition, because armature copper losses are not linear with current. They are in quadratic with current. It is IA square. Okay. When IA decreases by 2, armature copper losses decreases by 4. Okay. So here, armature copper losses at half the full load is 119 watts. Now, total losses. Total losses, I will take WM at half the full load is equals to, directly I will write 119 plus 399.1. Observe, my constant losses will not change. Okay, or for your convenience, we'll write the expression, then we'll write, because this is first example. Let us not be lazy in writing. IA half square RA plus WC. Okay. So this is the reason why we have calculated constant losses. Okay. I can, once I know the constant losses, which are constituents, which is composed of field current, shunt field losses, iron losses, and friction losses. Just by adding copper losses at that load condition, I will get the total losses, which is equals to 119 plus 399.1. It is 518.1. That's okay. Generator output. Sorry, generator input. P. P at half full load equals to P out at half full load plus losses. Sorry, this is WG, not WM. Please make a note that WG, because this is for generator. By mistake, we have taken this is WG. So WG at half full load equals to P out at half full load is 2100 watts. Plus 518 watts. Okay. Now, what were the total losses? In full load condition, it was 834. What are the total losses in half load condition? It is 518. So the losses have not been halved. Okay, the losses have not been halved. So we should remember all these are the observations you should be doing when we calculate anything in machines. Answers are not only the digits of mathematics. Every digit is speaking something. What you can observe here is even when I have halved the output, losses are not halved. 518 is not half the value of 3834. Okay. So as the load decreases, losses will be more prominent than output. Okay. Output is halved, but losses are not halved. They are more than half because of constant losses. Okay. So P in half is equals to, yes, how much?
2618.1.
2618.1. So efficiency of generator at half the full load is equals to P out half divided by P in half into 100. This implies 2100 divided by 2618.1. Okay. And also which is not half the input that is taken at full load. 2618 is not the half the value of 5034. Okay. So when the load condition is partial, less than full load, the output taken is more actually. More the input is utilized to satisfy the losses. So suppose observe here, the constant losses are 399.1 watts. Here. Hmm. We calculated, right? Yeah. Constant losses are 399.1 watts, or you take 399 watts. If I apply the input of 500 watts, out of 500, 399 watts is constant loss. If I apply the input of 1000 watts, out of 1000 watts, 399 watts is the constant loss. Plus copper losses we will get depending upon the line current. If I apply the input of 400 watts, 399 watts is the constant loss. Available power for copper loss and output is only 1 watt. So as we go on reducing the input, or as the load is lower than the full load value, constant losses will be more prominent and most of the input is taken to satisfy constant losses. Because of which my output will not be half of the input, or input will not be half of the output, half of the input at full load condition. Okay. Efficiency increases as the load increases. You might have observed the efficiency curve in the transformer. How will it be? Okay. If you plot the efficiency versus output, okay, it will follow like this. If you plot the efficiency curve versus output for any electrical machine, it will be the same. Whether it is generator, whether it is motor, for every electric motor, every electric machine, efficiency curve is this one. Whereas at one particular point, there is maximum efficiency. This is what efficiency max. Okay. So at this point, my variable losses become equal to constant loss and efficiency obtained will be maximum. And full load efficiency is always less than maximum efficiency. So whenever we are designing a machine, it is very much important for us what is the operating condition of that machine. Okay, what should be the operating condition of that machine is important. Now suppose you take a transformer, okay, which may be an additional point, but we should know. Suppose we take a transformer. Transformer is never operated at full load. Always, any transformer installed for operation is overloaded or is overrated. Suppose the existing load of a transformer, especially distribution transformers. Suppose a distribution transformer has to be installed in a locality where the load is say around 500 kilowatts. I don't install 500 kilowatts transformer there. I install at least 700 to 750 kilowatt transformer, so that in future load, if it increases, the transformer should be in a position to take that load, because transformers cannot be exchanged or replaced frequently. Now, when the load is 500 kilowatt, transformer rate kVA, transformer is 750 kVA, then what should be the operating point of a transformer? I should keep operating point of a transformer near to a maximum efficiency point. The load factor of a transformer should be such that it is always nearly equal to the maximum efficiency load factor. We know how to calculate load factor of a transformer for maximum efficiency. Okay, it is always equal to under root copper losses by iron losses. Okay, so that is the load factor. Similarly, even the same case is for motors also. Okay, so motors, if they are operated continuously, those can't be operated like transformers and generators years together continuously. Motors are always operated at certain intervals. Okay, then depending upon that, what load it is taking. If the motor is always to be operated at its full load, then I will try to keep maximum efficiency point and full load point near to each other. That has to be done in the design. These all things you don't learn in the design, because the design what you learn in coming semester is a very fundamental design process, a classical design process. But when you go to industrial design process, current in industries, they will think all these things. Okay, so it is very much important for me at what load factor any electrical machine is operating. If the load factor is less than maximum full load, that is, if the load factor is less than 1, then I try to keep the load factor for maximum efficiency and operating load factor near to each other, so that my economy will increase, losses will decrease. Okay, what is efficiency here? No, efficiency of generator at half full load
80.21.
80.21 percentage. Okay, so this is a Swinburne's test calculation for a DC shunt machine, I can say, not motor. Okay, because we calculated the efficiency both as motor as well as generator. Okay, so I will stop here because I have to discuss something about the lab. Okay, so is it clear? Any doubts in these calculations? Because it is first example, it appears very lengthy. Swinburne's calculations are very, very easy. Nothing. Okay, only we have to calculate copper losses. But many a times people will make mistake while calculating at partial load conditions. So that care you have to take. Okay, so what I will do, this page, whatever is there, this example page, 3 pages, I will send you a photo of this in the class group, because these calculations you need for lab calculations. Today you will be conducting virtually Swinburne's test, okay, in the lab. So with this, I will end this session. Please don't leave. Still attendance has to be taken and some instructions are to be given.